Yeah, as an announcement, yeah, we will have an exam exactly in a week, right? Next Monday, starting from noon. And yeah, as announced, yeah, it will have many true-false exams, and I believe my TAs have posted some homeworks, including those true-false problems in the book. So it will be sufficient to be able to understand and be able to correctly answer the true-false questions in the book. Okay. But at the end of each subchapter, such as 2.1 or 2.2 or 2.3, it will have some exercises and true-false problems. But yeah, please be sure to cover those problems at the end of a big chapter of chapter 1 and chapter 2. So there are some supplementary exercises, right, at the end of each chapter, not at the end of subchapter. Okay, so there are some supplementary supplementary exercises that covers the content of the entire chapter. So they also have a true false questions, and also those questions are usually trickier than those true false questions of the subchapter problems. Okay. Any questions about the exam? 네.
Will we not be given any of last year's problems?
Yeah, we'll discuss. I'll discuss with my TA. Yeah, whether we can. Yeah, whether we can distribute those previous exams. Yeah, but yeah, I'm not sure at this point. Okay. Any other questions? Right. Okay. Okay, so last time last time this theorem 7 was the main part that we studied. Okay, so the main point of this theorem is, so if the matrix is invariable, of course it is a square matrix, and this theorem says the invariability is equivalent to having the row reduced echelon form as identity matrix, right? So we didn't do the formal proof, but I think I gave you enough or sufficient intuition. So if this matrix is a row equivalent to identity matrix, and then it means we have the pivots in every row and every column by the shape of identity matrix, or by the pattern of identity matrix, right? Okay, so let's see. So in that case, yeah, we can consider the elementary matrices corresponding to our row operations, right? So we basically studied or learned that we can always represent each row operation as a matrix multiplication on the left of the original matrix of E1 and E2 and so on. These are called elementary matrices corresponding to row interchanges and row scaling and row replacement, right? And then suddenly, by the fact that we converted A into reduced echelon form, and then we suddenly obtain this product of the matrix that is multiplied on the left of matrix A that will produce identity matrix, and so it gives us the matrix C that satisfies this guy. Okay, so this guy was the main definition of identity matrix. And as I mentioned last time, if we consider the square matrix, and then even if we didn't prove, this matrix C will automatically satisfy this equation as well. Okay, so we don't need to worry about whether one being possible. I mean, one is possible, but the other is impossible. So there is no such cases in the case of square matrix. Okay, so in this case, this guy works as our inverse matrix of original matrix A, and more importantly, E1 through EP are all, each of these elementary matrices are all invariable, right? And so its inverse matrix, which is this, so this guy inverse is actually our matrix A, okay? And then this can be further written, as E1 inverse, E2 inverse, and EP inverse, right? Okay, so that's how we proved that if this matrix is a row equivalent to the identity matrix, and then this matrix is invariable. And in the case of the opposite direction, where A is invariable, if A is invariable, and then it leads to the reduced echelon form of identity matrix. How can we prove it? So in that case, this matrix A is invariable, and then we studied that in the previous theorem, that if A is invariable, A inverse is always exists, and then given this linear system, and then this solution X for this linear system is represented always as this form, right? Regardless of any B, right? Because we can simply multiply A inverse on both sides, okay, regardless of any B again, and then X will be always obtained as this form. So X has this closed form solution, or always A has always this representation, and so we can conclude that the solution always exists, right? And then we know that for any B, if we can guarantee the solution always exists, at least for one or more solution, and then it means we have a pivot in every row. And so in the case of square matrix, having the pivots in every row, it will be, I mean, the only possible form will be the identity matrix for its reduced echelon form, right? So again, it guarantees the existence of the solution for any B, and then it leads to the pivot existing in every row, and it is also equivalent to the reduced echelon form of an identity matrix. Okay, so that's how we prove this theorem. Okay, and then let's move to the next chapter. So any questions so far? Okay, and then now we will study one big theorem that that includes all the things that we studied before. So some of them are already what we already covered, and some of them are some additional stuffs that we have to think about. So it is saying that we consider only the square matrix again, and then it is saying all the items are equivalent. So the first item is A is invertible matrix. Okay, so this guy is equivalent to any other items that we have in this theorem, and also this theorem is not described in a single page, but it goes up to the item L. Okay, so from A through L, all of them are equivalent. So that is the main point of this theorem, and then let's view what each item is describing. Okay, so in order to prove all items are equivalent, we basically utilize some kind of ring kind of structure in our proof. Okay, so the first ring that we want to follow in order to prove some of these theorems are shown in this form. So it is saying, this arrow indicates that if A is true, and then J is always true. Okay, so 명제가 영어로 뭐죠? statement? statement요? 맞아요? preposition? proposition? preposition 전치사죠? proposition? 네. Okay, so we consider this kind of proposition, which is indicating that if A is true, okay, then it is always true. I mean, this J is always true. Okay, so it's like, okay, so A is maybe the statement A is like X is maybe a natural number. 네, 이게 자연수죠, 자연수. And then X is an integer. Okay, so it's quite trivial example, but this is one example of this proposition. So if this is true, and then it always guarantees that this second statement is true. Okay, so this 네, 이거 맞아요. 네. 네. So in other words, A is a condition for J. So I'm gonna make it as a multiple choice problem. Necessary or sufficient? Which one is true in this case? Sufficient, right? Sufficient. Okay. So here the answer is sufficient. 이거 뭐 충분 조건이라고 하죠? 충분 조건. 그리고 이제 의미는 뭐 J라는 것을 만족하기 위해서는 A를 만족하면 이게 차고 넘친다 이거예요. 그래서 이제 충분하다라는 얘기가 되고, 그래서 A가 더 하여튼 스트릭트한 컨디션이라는 거죠. 그래서 A를 만족하면 무조건 J를 만족하는 것이고, 둘 중에 뭐가 좀 더 스트릭트한 컨디션이냐? A가 더 스트릭트한 컨디션이죠. So the condition or the statement A, okay, is much more strict. I mean, more strict condition than J. So that A is satisfied, and then it always guarantees that J also satisfies. Okay, and also we think of true set. Okay, true set. 뭐죠? true set이? truth set. 진리지파. So the true set that satisfies this this X satisfying the condition A, for example, and J, yeah, we can think of the true set for A and true set for J. So in this case, yeah, the true set for A is contained or included in the true set of J, right? So that is the meaning of this sufficient condition. So if A is satisfied, and then it guarantees that the true set is always included, or the subset of the true set of J. Okay. Right. So back to this ring. So in this case, if A is true and then J is true, and then if J is true and then D is true. Okay. So this is how we prove some of these theorems that we are given, and then the true set for A should be included in the true set of J, and then also the true set for J should be included in the true set of D, right? But at the end, so this true set for B will be the biggest one, containing all the true set of B and then D, J, and A. But the true set for B is included in the true set A. So the only possible way will be to have all the same true sets for each of these conditions. So they are all equivalent condition. Okay, so that's the overview or brief sketch or how to prove this theorem. Okay, right? Then let's follow these items: A, J, D, C, B. Okay, so A and then J. So we can see that J is part of the requirement by the definition of this inverse matrix, right? So if A is true, and then J is obviously true. Okay, and then we move to D from J. So D is saying this has the trivial solution. Okay, so from this fact, how can we prove that this AX has only the trivial AX equals 0 has the trivial solution? Okay, right. So let's consider let's assume that there exists some non-trivial solution X. Okay, in that case, this X is non-trivial solution. So this is our kind of initial assumption. Okay, and then let's just multiply this by C. Okay, by this fact. Okay, by utilizing this, we multiplied C from this homogeneous linear system. In this case, this becomes identity matrix, and this becomes 0, right? And so it leads to X being 0 vector, right? And so it violates our assumption that, it violates the possibility of having non-trivial solution. Okay, so that's how we prove, starting from this assumption given in J, and then we prove this statement in D. Okay, so the true set for D will be bigger than the true set of J. Okay, so A, J, D, and then let's move to C, B. Yeah, J. So moving from D to C and to B and A, so these are, okay, so moving from D to C, in this case A is a n by n matrix, and then it has, this homogeneous linear system has only the trivial solution, and thus it has the pivot position in every column, right? And so we have n column, and so we have n different pivot positions, right? And so we can easily prove that C is true if D is true. And then moving from C to B, yeah, if A has an n pivot positions given a diagonal matrix, and then having n pivots at every column, having a pivot in every column, and then the only possible pattern of our matrix will be the identity matrix by the shape of this square matrix having the same number of rows and columns, right? Okay, and then A is row equivalent to the identity matrix, and then A is invertible matrix. Why is it true? We proved it in this previous theorem, right? Okay, so we arrived back at the A. So we proved A, J, D, C, and B are all equivalent. Okay, and then the next loop is A, K, G, A. Okay, A, J, D, C, B, A. And then the next loop is A, K, G, A. Okay, so now we start with the new loop, starting with an A as well. A, K, G, A, and then A from A to K. So K is also part of our definition of inverse matrix, right? So we can easily move to K from A, and then let's move to G in this case. So here, this is one interesting kind of proof problem. So this is part of the definition of the inverse, and then how can we prove that if K is satisfied and then G is also satisfied? So G is saying that AX is equal to B has at least one solution for any B. Okay, so it guarantees the existence of the solution for any B. Okay, so here, so let me show one little trick. Okay, so X as let's consider this dB. Okay, so D again is our inverse matrix. Okay, satisfying this equation, and then given this linear system of AX is equal to B. Okay, and then we considered some arbitrary representation or particular representation of dB. Okay, so this is a kind of smart choice, and then let's plug this X into AX. Okay, and then it will be equal to AdB, right? And then AD is identity matrix. Okay, and so we obtain B over here. Okay, so we didn't have any reason to set X as this dB, but this is just a random and smart choice. Okay, but if we set X as dB and then plug it into AX, okay, and then if we rewrite it, then it will give us B, right? And so we at least found one solution that satisfies this. That is represented as dB. Okay, and then we can see that this guy is always the solution for our linear system. So we found at least one solution in this form, satisfying this linear system, and so we can guarantee that there exists at least one solution. Okay, and also we also studied that in the case of a invariable matrix, and then the solution will always exist as, so given this linear system, and if A inverse exists, and then A inverse A and X is equal to AX inverse B, and then X is equal to A inverse B, right? And so this guy can be defined for any B, right? And so that's how there's a different method to prove the existence of the solution of this linear system for any B, right? Okay, and at the same time, this also says that the solution is always unique, right? But anyways, from K to G, we were able to prove it by just plugging X as this dB. Okay, so we moving from A to K, and then we arrived at G at this point, and AKGA. Okay, and then now how can we move from G to A? In this case. So in this case, G is saying that the solution always exists for any B, and then we cannot directly move from G to A, but we also go to A through the B. So in this case, if G is true, and then we can see that the pivots exist for every row, right? So that was the part of the previous theorem, right? So having the pivots in every row of an A, okay, so that is equivalent to the condition that this AX is equal to B has always the solution for any B, right? So in that case, we also we still consider the square matrix, and so having the pivots in every row and then its corresponding reduced echelon form will be identity matrix. Okay, so moving from G and then to B, okay, and then we can arrive at the A, right? Okay, so now G is in our circle. Okay, so this circle and the AKGBA is another circle that we proved. Okay, and then now let's view this GHI and DEF. GHI and DEF. So this G and H, the columns of an A spans Rn, or the span of the columns of an A is equal to Rn. Okay, so that is another equivalent condition to G. So that was part of our previous theorem. So we are basically talking about the theorem in. Does anyone know which chapter contains that theorem? Yep, this one, right? So we are talking about this theorem 4. So we already studied that all these items are equivalent. Okay, so this guy is the same as H, which says the span of the columns of an A is equal to Rn if G is satisfied. And then from the perspective of this linear transformation, so we studied about the onto and one-to-one, and these two conditions are also equivalent to the condition of onto, right? Because the range of this transformation defined by AX is basically the columns, the span of A1 through AN, right? And then onto means this guy is completely cover up our codomain of Rn. Okay, so GHIR all equivalent, right? And so GHI are equivalent. And then now let's move to D, E, and F. So these are about the linear independence, right? So having only the trivial solution for homogeneous linear system, and then that is equivalent to the situation that the columns of an A are linearly independent, right? So that was part of our definition of our linear independence. And also that is related to this notion of one-to-one, right? So one-to-one condition for the linear transformation of AX. Okay, so that is equivalent to the linearly independent columns of an A, right? So which one is not marked yet? The only item is L. So L is saying that A transpose is invariable matrix. So I think I already proved it. So if A is invariable matrix, and then A and let's denote it as A inverse for the inverse of an A. Okay, so in this case, if we transpose it, and then by the property of the transposition, A inverse transpose and A transpose is equal to identity transpose, which is the same as identity matrix. Okay, and so now we found the inverse of A transpose as this guy, right? Because that is multiplied on the left and then created or formed the identity matrix. So A inverse transpose is our inverse matrix of A transpose. Okay, so the inverse of an A exists, and then the inverse of A transpose also exists. Okay, so that's the theorem L. So A, in other words, A is invariable matrix. Okay, and then starting from A, we can arrive at the L. Okay, A transpose is an invariable matrix, and we can also prove the other way around, right? So if the inverse of A transpose exists, and then also A inverse will also exist, right? We can do this. We can do the same proof by starting with A transpose, and then some inverse matrix being identity matrix, and then applying the transposition on this equation, and then we can obtain the inverse of an A. Okay, any questions about this theorem? Okay, so I didn't give any overview or the intuition about this really long and big theorem, but let's just discuss briefly about the intuition or the main kind of point of this theorem. So we partly discussed some of these theorems already, but if your matrix, if we are given a square matrix, and that square matrix is invariable, and then it satisfies virtually all the conditions that we studied. So if A is invariable, and then the pivots exist in every row and also every column, and so AX is equal to 0 will have only the trivial solution because of this existence of the columns in every column. Existence of every the pivot in every column. Okay, and AX is equal to B will be guaranteed to have at least one solution because of the pivots existing in every row. Okay, so basically invariable matrix will have a pivot in every row and every columns, and so that will lead to all the corresponding properties or characteristics of the existence and the uniqueness of our solution. And also from the perspective of linear transformation, it will satisfy both of these onto and one-to-one. Okay, and yeah, I think pretty much the main point of I think that is pretty much the main point of our theorem. Any questions? Okay, and then let's think of this onto and the one-to-one conditions from a slightly different perspective that we studied last time. So in the case of an onto, in order to satisfy the onto condition, let's call this a domain as D and the codomain as C. These are the set of vectors, and so the notation of this is indicating the number of elements in the set. Okay, so suppose yours. Okay, so D is 1, 2, 3, 4, and C, which is our codomain, is 1 through 10. Okay, and then what is bar of D, or that is called a cardinality. Okay, so that is the mathematical name. So this is simply the number of elements in the set. So how many elements in the set? It's 4, and it is 10, right? The number of elements. Okay, so that is what this notation of this single bar enclosing this set is meaning, right? And so here, we can easily see that in order to satisfy at least onto, okay. So again, in terms of an onto condition, we know that, let's call this as maybe X and Y, because that will be more intuitive. So in order to satisfy onto, which one should be bigger? The left or right? Left, right? Because we have to hit at least one, hit every element in the codomain at least once. Okay, it doesn't matter if we hit the particular element twice in the codomain, but at least every element in the codomain should be hit at least once, right? Okay, and then what is the condition of one-to-one? So in the case of one-to-one, I mean, it can have the same elements. So this is the is it the necessary or the sufficient condition to satisfy one-to-one? Is it necessary or sufficient condition? Necessary. Sufficient. So if this guy is sufficient condition, and then it always guaranteed that the transformation is one-to-one. But is it actually true? It is not, because this is not sufficient to satisfy, this is not a sufficient condition to satisfy one-to-one, right? So it is just a part of the condition to satisfy in order to satisfy one-to-one, right? So that way it is a necessary condition but not a sufficient condition. Okay, so anyways, this is a necessary condition to satisfy 1-to-1, right? And how about satisfying both of these 1-to-1 and onto? So in that case, the only possible case will be this guy, right? And again, is this a necessary or sufficient condition for satisfying both of these onto and 1-to-1? Necessary? Sufficient? It's a still necessary condition to satisfy both of the onto and 1-to-1. And why is it so? I mean, can we guarantee that? I mean, by based on the fact that this condition is satisfied, can we guarantee that the mapping is 1-to-1, both the 1-to-1 is onto? It is not. I mean, it is only part of the condition, right? Yeah, because like 1, 2, 3, 1, 2, 3. So this is at least satisfying this guy, right? But what about this guy? Is it onto or 1-to-1? It says satisfies neither of them, right? So this is a necessary condition, okay? Right? But at least we know that this is a necessary condition, right? And then back to this case. If our matrix is a n by n square matrix, and in the case of a square matrix, and then from the perspective of this linear transformation, and then it is mapping n-dimensional vector into n-dimensional vector where A is n by n matrix. Okay, so in this case, we can see that the cardinality or the number of elements in our domain is the same as the codomain, right? So at least in case of this square matrix, then it satisfies some necessary condition of the it satisfies this necessary condition to be able to satisfy onto and 1-to-1, but that's not a sufficient condition. And then what is the additional condition to satisfy in order to satisfy both of these onto and 1-to-1? That is this guy. Your matrix A is invariable. Okay. In that case, your matrix satisfies onto and 1-to-1. And let me ask another question related to that. Given this square matrix, okay, square matrix having this condition, can we satisfy 1-to-1 but not onto? So can we satisfy only one of them but not the other? Right? So 1, 2, 3, 1, 2, 3. So in this case, let's make it satisfy 1-to-1, for example. Maybe this one, or maybe this one. And we can think of many, several different cases of satisfying 1-to-1, right? But in this case, can we not satisfy onto? While satisfying 1-to-1. So in this case, as we can see, if we satisfy 1-to-1, onto will automatically be satisfied, right? Because of this fact, okay? So we have the same number of elements in the domain and the codomain, and if it is 1-to-1, okay, and there is no redundancies in the elements in the codomain that gets multiple hit. So there is no such element, right? And so they will be mapped basically 1-to-1, and then it means every element will get hit exactly once in the codomain, right? So onto is always satisfied. And at the same time, if onto is satisfied, and then can we not satisfy 1-to-1? So it is also impossible. So okay, so in this case, 1, 2, 3, 1, 2, 3. So let's try to make it satisfy onto. Okay, onto means, okay, so in this case, suppose this guy was mapped into 1. Okay, and then suddenly there becomes no hope. I mean, there is no hope to satisfy onto, because we have no additional elements in our domain, right? So we cannot allow any redundancies, right? And so the only possible way, yeah, while satisfying onto, I mean, and then one-to-one should be automatically be satisfied. Okay. So this kind of, yes, a simple toy example will also hold, I mean hold true in the case of n by n linear, I mean, yeah, square matrix, and it's a linear transformation. Okay, so we can roughly, yeah, even if, yeah, even though, or although their number of elements are all infinity or infinitely many, but by the fact that they are living in the same, I mean, they are same dimensional space, and so yeah, we can think that their elements, number of elements are the same. And in this case, we can see that if they satisfies only one-to-one, and then it will automatically satisfy onto as well. So there, yeah, it is always true, right? Okay, so back to this theorem. Okay. Yeah, there was a one-to-one condition, and also there was onto condition, and those two are satisfied. Okay, and also the existence of our solution for any v, and the uniqueness of our solution for the homogeneous linear system, then these are all equivalent as well. So if one is satisfied, and then all the others are satisfied. Okay, and at the same time, if any one of them, okay, you choose any one of them, and then if that one is not satisfied, and then it automatically make all the others not be satisfied. Okay. So they have all the same destiny. Okay, so that's the meaning of this equivalence. So if any one of these items is true, and then all the others are also true, but if any one of them is false, and then all the others are also false. Okay, but again, this kind of properties is only applied to the square matrix. Okay, so we consider only the square matrix. So again, if A is not square matrix, and then the matrix can have for example, linearly independent columns, but at the same time, I mean, A can have linearly dependent columns, but at the same time, we can have the pivots in every row, which guarantees the solution for any B, right? So in that case, the linear independence and this having the pivots in every row, I mean, those two conditions may not be satisfied simultaneously, right? And actually, if we consider the rectangular matrix, actually only one of these two types of conditions will be satisfied, right? So yeah, we already discussed that. So if our matrix is a little bit fat and short matrix, and in that case, it is possible that we have pivots in every row, but not having the pivots in every column, because simply we have more number of columns than the number of rows, right? And what about this case? In this case, so there is a possibility. I mean, having a linearly independent columns is possible because we have 3 columns, but can we guarantee, I mean, is it possible to have a pivot in every row? It is impossible, right? Because the maximum number of pivots is only 3, which is the number of columns, right? And so we have more number of rows, which are 4 rows, and so we cannot have the pivots in every row. right? So between these two types of conditions, only one of them, yeah, can be satisfied, but not the other sets of conditions. Okay. But at the same time, in the case of a rectangular matrix, those two types of conditions, may not be satisfied. Any of these conditions may not be satisfied. So for example, if we have a pivot in, for example, in this case, okay, suppose this is our echelon form. So in this case, we don't have a pivot in every columns, and also we don't have a pivots in every row, right? In this case, linearly dependent columns, and we cannot guarantee the solution for any b because we don't have a pivot in every row. Any questions so far? Okay, then let's take a break for 10 minutes and resume at 1:05. 네.
공부하다가 갑자기 드는 의문인데
네.
이제 linearly independent columns로 이루어진 매트릭스가 있으면
네.
이제 저희가 뭐 가우시안 엘리미네이션 다 하고 나면 이제 0, 이게 0 이제 row 벡터가 존재하지 않게 되잖아요. 네, 근데 이게 calculation으로는 그렇게 뭐 결과적으로 나오는 건 당연히 알겠는데 그냥 이게 좀 궁금한 게
네.
컬럼들이 linearly independent 한 건데 결과적으로 row도 같이 linearly independent 한 게 보이게 되는 건데 이게 왜 그럴까가 계속 그냥 계산하면 그렇게 되는 건 알겠는데 왜
잠깐만요. 질문이 그러니까 linearly independent한 컬럼을 가지는 매트릭스가 있고,
네, 그래서 얘네들 계산을
네.
하게 되면 결국에는 row들이 다
네.
이제 얘네들로 다 서로
로우들이 linearly independent 해진다고요?
그런 결과가
그래요? 그런 경우가 있어요? 어디 있어요? 그게?
뭐 여기 있던 내용은 아닌데 그냥
네.
계산을 하다 보면
그래요? 이게 그러니까 여기서 지금 이게 이렇게 있으면 linearly independent 하잖아요. 그쵸? 근데 지금 이 로우들도 linearly independent 하다는 거예요?
스퀘어 매트릭스에서
스퀘어 매트릭스? 네네. 오케이. 네. 오케이.
이제
오케이. 네. 오케이. 그러니까 컬럼들이 리니얼리 인디펜던트한데 그러면 왜 로우도 리니얼리 인디펜던트해지냐? 스퀘어 매트릭스에서.
네.
뭐
피벗이 존재하고 뭐 그래서 이제 그렇게 되는 건
네.
이렇게 숫자상으로는 그림상으로
네.
알겠는데 그냥 지오메트릭한 그저 조금 한 단계 더 나아간
네.
그 의미가 좀 있을 것 같은데.
그래요. 네. 일단은 그 지오메트리컬리 뭔가 이제 그 좌표 공간상에서 그거를 조금 바로 이해하기는 좀 어려워요. 그러니까 이게 매트릭스가 그러니까 컬럼 벡터들과 그 컬럼 벡터들이 뭔가 스팬이나 아니면 리니얼리 인디펜던트 하냐 디펜던트 하냐 그런 개념이 있고, 그다음에 로우 벡터들, 우리가 매트릭스 갖고 있는 로우 벡터들이 있을 때 그 로우 벡터들에 역시 또 스팬이나 이제 리니얼리 인디펜던트 하냐 안 하냐 뭐 이런 요소들이 있는데, 근데 그 두 개, 그 컬럼 벡터들의 스페이스와 로우 벡터들의 스페이스는 기본적으로는 약간 좀 어떤 직접적인 관련은 바로는 없고요. 근데 다만 그게 왜 그런가를 좀 그냥 이해를 해보면, 그 일단은 A가 저기 인버터블한 매트릭스여서 이제 그 컬럼에 모두 피벗을 갖고 있으면, 그러면 A가 인버터블하다. 근데 이제 여기서 나왔던 것처럼 A 트랜스포즈도 인버터블한 거잖아요. 그러면 A 트랜스포즈도 역시 인버터블하다는 거는
로우도 같이.
그렇죠. A 트랜스포즈에서 로우가 A에서의 로우가 이쪽에선 컬럼이 되니까 이쪽에서도 하여튼 얘도 인버터블 하니까 얘 이제 리듀스 에슐론 폼이 아이덴티티 매트릭스여서 이제 각 컬럼들이 이제 그 피벗을 가질 거란 말이죠.
이게 약간 근데 계속 공부하면서 느낀 건데, 만약에 저희가 뭐 A 뭐 B에 대해서 궁금을 하게 되면 이제
B요?
어디가 뭐 어떤 관계도 해서 뭐 어떤 B라는 뭐 명제가 궁금해지면 뭐 A면 B다 이걸 증명하게 되는데, 이제 또 근데 또 A가 궁금해지면 또 B이기 때문에 A다 하는 그런 좀 내용들이 많은 것 같은데.
아, 그래요? 그 부분은 그러니까 그러니까 그 부분은 뭔가 증명이 제대로 안 된 것 같고, 내 생각엔 그 예제가 있으면은 알려주면 내가 좀 해결을 해줄 수 있을 것 같아요. 네.
막 엄청 큰 건 아니고 이게 스퀘어 매트릭스면은 스퀘어 매트릭스고, 이게 인버터블 어쨌든 가역 행렬이니까 여기 다 이게 그 항등행렬 그 i랑 똑같을 거 아니에요. 그래서 여기 AX는 자명한 해뿐인데 AXB는 적어도 하나의 해를 간다 했잖아요. 근데 이게 말은 이렇게 해서 사실상 해 하나밖에 없는 거죠.
그렇죠. 맞아요. 그게 맞아요. 그러니까 여기서 이렇게 쓰긴 했는데
엠리스트라고 해가지고 약간 뭐 다른 경우가 있나 싶어서.
그러니까 이것도 만족해야 되고 그러니까 이것도 해가 하나가 있는 게 맞아요. 그리고 그 띠어럼이 아마 2.2였나 아니면 2.1이었나에 그게 있었잖아요. 그러니까 이게 보자. 요 띠어럼이 뭐냐면
하나밖에 없다.
맞아요. 이거 하나밖에 없다는 이 띠어럼이 있었듯이 이게 맞는 말인데, 이거가 그러니까 여기서의 이 말이 틀린 건 아니죠. 이게 좀 더 넓은 컨디션이니까 이것도 만족하고 또 동시에 저것도 만족하는 거예요. 해가 트리비얼 솔루션밖에 없다. 그리고 해가 적어도 모든 B에 대해서 다 일단 하나 이상은 존재한다. 근데 실제로 그 두 개 조건이 이제 이퀄밸런트 하다는 거는 결국은 해가 유니크할 수밖에 없는 거예요. 네. Right, let's continue. Okay, so I think it's quite important to understand this theorem intuitively, although so many items in this theorem is quite daunting to study, but if you have a high level understanding, then yeah, it is quite simple, right? Okay, so let's apply this theorem into some of these examples. So this example is saying is to ask to determine like whether this matrix is invertible or not. Okay, so in order to determine whether this matrix is invertible or not, then we can simply check whether its echelon form or reduced echelon form is identity matrix. So still our mechanical computation is just Gaussian elimination. So once we do the Gaussian elimination, and then we obtain this pivots along the diagonal, right? And then even before converting it further into reduced echelon form, and then by the pattern or by the position of this pivots, and then we can easily see its reduced echelon form is identity matrix. Okay, and by the way, yeah, just to help you start, prepare for the exam. Yeah, I think I mentioned that. Yeah, it's just a review. Yeah, review of what we studied, but echelon form is echelon form unique or not for a particular input matrix? So echelon form is not unique, right? So this is an echelon form, and then how about this 2 and 8? So this is also another valid echelon form of this original matrix, right? But reduced echelon form is always unique, okay, for a particular matrix. And also, I think I forgot to mention one additional thing in our see. Okay, related to this theorem, we studied about how to obtain our inverse. So how we obtain our inverse is as follows. So we have original matrix A, and then we put identity matrix on the right, and then do the row reduction or Gaussian elimination to obtain this matrix as identity matrix, and then this one will be naturally our inverse matrix, right? So why? The reason why we do so is because even though let's see. Even though E1 through E10, for example, and then if we obtain the identity matrix. So in this case, we just started from the single identity matrix and then perform our reduced echelon form until we obtain identity matrix, right? And then this part, okay? So we form explicitly our elementary matrix for the first step of a Gaussian elimination and the second step and so on. And then once we multiply all of them, and then it will be our inverse matrix, but we actually don't do so, right? Because explicitly forming our E1 and E2 and so on, so there will be kind of additional kind of effort that we have to put, right? So in order to avoid putting this additional effort of explicitly forming E1 and E2 and so on, and then computing their product, okay? So we don't do it actually. We actually put the identity matrix and then do the row reduction on this big augmented matrix, okay? And then naturally this part will be just your inverse matrix, because where is it? So yeah, over here, right? So if we put the identity matrix as a kind of augmented part, and then if we just do the row operations, and then even if we don't explicitly form E1 and E2 and so on, okay, this part corresponding to identity matrix part, okay, so that part will be the product of our elementary matrix, right? So that's how we easily obtain the identity matrix without explicitly forming our elementary matrix, right? Right, so this will be possibly one kind of candidate example that you see in our exam. So compute the inverse matrix, or maybe 3x3 matrix. I will not probably give you 4x4 matrix, because it is just a matter of a kind of computation. So, but anyways, additional stuff that I wanted to mention over here is, so what is the meaning of putting or forming this augmented matrix? Okay, so in this case, let's see. Yep, so we want to obtain A inverse, and then let's call that as C, and then that is forming the identity matrix. Okay, and then suppose we have A as 3x3 and also C as 3x3, and then identity matrix will be 1 1 1 0 0 0, right? Okay, so we have an A over here, and then from the column combination perspective, so A times this guy, and then you guys know that the column, 3 columns of an A, so we have 3 columns in A, and then using the linear combination coefficient over here, right, and then do the linear combination of these columns of an A, and then what does it produce, or what's the result of it? So the result will correspond to the first column of the resulting matrix, right? So that's what we studied in the 4 different perspectives of matrix multiplication, right? And then the second set of linear combination coefficients, by using the same set of columns provided in A, and then that will give us the second column in the resulting matrix, right? And then let's call this C1 and C2 and C3 as the 3 columns of C, okay? And then we can decompose this guy into A C1 is equal to what? 1 0 0, and A C2 is equal to 0 1 0, A C3 is equal to 0 0 1. Right? Any questions about it? So you guys follow this, right? 이거 알겠죠? 표정들이 안 좋네. 알겠죠? 시험 문제 나올 것 같아요. 내가 특별히 내 이야기 해주는 거예요. 과거에 내 나왔던 기억이 있어서. 알겠죠? 뭐 모르겠어요? 모르겠으면 다시 설명을 해주고. 알겠죠? 표정을 읽을 수가 없네. 다들 복화를 해야겠는데요. Right, so we can understand this from this relationship we can see that, for example, the second column of our inverse matrix of an A. So if our question or our problem, probably in our exam, okay, so instead of, you don't need to obtain the full inverse matrix, but I only want the second column of the inverse matrix of an A, okay? And then give that second column of an inverse matrix. And then how can we solve this problem? We can only solve this linear system instead of obtaining all the inverse matrix, right? Because from this example, each column is computed independently, right? Right, so in this case, 1, 2, 3, 4, 5, 6, 7, 8, maybe 10, in order to make sure this is an inverse matrix. And then, we put this 0, 1, 0 as our augmented part or B part, and then perform the row reduction. And then our solution will be the second column of our inverse matrix. Does it make sense? Okay, so I'm not sure whether it would, this kind of problem is included in our exam or not, but that's some good stuff to know. Okay, so back to our chapter 2.3. From the perspective of this linear transformation for this square matrix and also invertible matrix, and then if the matrix is invertible, and then AX, okay, Y is equal to AX is, okay, so that is both 1-to-1 and onto, right? So we studied that. And in that case, from the perspective of a transformation, that mapping can be said as invertible, or the mapping is, the inverse mapping exists. So inverse transformation in Korean, 역함수라고 그러죠. 역함수. 그러니까 함수의 측면에서 이제 역함수가 언제 존재하느냐, 역함수가 존재하려면 어떻게 해야 되느냐, 일단은 1-to-1 및 onto를 만족을 다 해야지 역함수가 존재해요. Okay, so in order to be able to define the inverse transformation, so for example 1, 2, 3 and 1, 2, 3, and for example 4. So in this case, it is clearly not the case that satisfies both of the onto and the 1-to-1, right? So for example, like in this case, so the inverse mapping cannot be defined, because in the inverse mapping, so this is domain and the codomain, but the domain, their kind of roles are interchanged, right? So this one becomes our domain, right? And then this arrow gets reversed in terms of their direction, right? But in this case, one of the elements in our domain in the inverse mapping doesn't have any function value or function output, right? And also, if 2 is mapped into 1 at the same time, and then in this case starting from 1, so it is shooting the arrow twice, right, from a single input value in our domain. So it violates the basic condition or requirement of our function. So 1-to-1 and the onto is basically the sufficient and the necessary condition or equivalent condition to be able to define the inverse mapping or inverse transformation. And what is that inverse mapping? Simply, the inverse mapping is A inverse Y is equal to X, right? So this guy is inverse mapping. So some vector is transformed or mapped by our matrix A, and then if A is a square and the invertible, and then it's inverse mapping is defined because this mapping is at least 1 to 1 and onto, and then that inverse mapping is defined as A inverse. It's quite obvious. Okay, so that is about this theorem 9. Right, any questions so far? Okay, and then that's it for this chapter 2.3, and then now move to chapter 2.5 about this matrix factorization. So matrix factorization, this factorization in Korean, 네, 이걸 뭐라고 그러죠? 한글로? 한글로는 이게 뭐에 해당이 되냐면 인수 분해라고 해요. 네. Okay, so factorization in Korean is the same as 인수분해. And then yeah, so what is this factorization in the case of polynomials? For example, x squared minus 2x minus 3. And then in this case, we basically decompose this given expression into the product of some, into a product of some multiple expressions, right? So basically, we rewrite it as the product of multiple stuffs. Okay, so in the case of matrix factorization or matrix의 인수분해는요, so we are given a matrix A, and then we want to be able to represent this guy as the product of some matrix B or C, B times C, or B, C, D, and and things like that. And if you start to study this matrix factorization, and then it actually opens up all the elegant and quite high level linear algebraic techniques. So there are many different matrix factorizations, such as the LU factorization that we study, and also eigen decomposition, and singular value decomposition, and Cholesky decomposition, and QR factorization, and so on. So there are so many, and all these techniques are so useful in many of different fields, including machine learning and artificial intelligence, and so on. And probably if you just mastered eigen decomposition and singular value decomposition, and then you will be probably done for the undergrad level linear algebra. Although we will not cover all of them within a single semester, which is sad, but if you're interested, and then you can continue studying about these interesting matrix factorizations. And for example, in the case of machine learning, just to give you an interest, although it's a quite old techniques, but so these figures are the result of the matrix factorization when using the input matrix as a collection of all the images that we are given for the facial images. So how do we represent images as the matrix? So it's quite an off topic, but let's see. Right, so let's consider the facial images, and then suppose this guy is maybe 3 by 3 size of pixels. Okay, so although the resolution is ridiculously low, and the actual images of that we see has much higher resolution, but suppose this one is 3 by 3 size. Okay, and then we can consider its pixel values like this. Okay, ranging from 0 to 255, and also this is a kind of color images. So at each pixel, okay, and then it has RGB value. So so this is not just a single pixel, but if we just take the average of it for each location or each position of these RGB values, and then we can consider it's a grayscale version of this image, okay, making it as a black and white image, okay. And in this case, we can think of this as grayscale pixel values, and then simply we can represent it as this single vector, okay. So we just chop them off column by column and then put it over here, and then we obtain this single vector representation, and which dimensional space is this image living in. So it is living in 9-dimensional space, right? And then suppose we have another image, and then likewise we can represent on its own 9-dimensional vector representation with respect to its pixel value, right? So it's it's basically the starting point of all the machine learning and the artificial intelligence kind of tasks, because so for example, suppose you have a bunch of data collecting person's height and weight, okay. So maybe Jane is 155 tall, and then maybe it's 50 kilogram. I'm not sure whether it's overweighted or underweighted, but and maybe John 170 and maybe 75 kilogram and so on, okay. And then these are called a feature vector representing each data item. And then suppose this guy, we want to be able to predict whether this person has a diabetes or not, or will have a diabetes in maybe in the coming 10 years. And then suppose we collected all the past data, okay, so past samples from some hospital, and having this record, and this guy turned out to have a diabetes and not having the diabetes and so on, right? And so this is an initial settings for the machine learning problems, and these ones are input information to be utilized to determine whether this guy has diabetes or not. So overall, suppose we have 100 different people, and then maybe some taller guys didn't have a diabetes, but mostly although it's sad, but the shorter guys had a diabetes in our record, okay. In that case, we can see these kind of common patterns, right? And then also this pattern may not be may exist when considering both of these values as well simultaneously. For example, just looking at the height itself may not be enough. We may have to think of kind of relative kind of degree of an overweightedness by considering both of the height and weight, right? So in that case, we have to consider both of them simultaneously, whether this guy is a little bit overweighted or underweighted with respect to the average kind of patterns. And then suppose that influences a lot whether this guy has a diabetes or not, okay. In that case, our machine learning algorithm will capture these patterns so intelligently. And so, but anyways, these are input information, and so these are the input feature vector. So this is like a height and weight and maybe blood types, and this guy is has an age and so on. So these are kind of considered as a feature vectors. So what is the height in this case, or the first dimension? What is the meaning of the first dimension? First dimension is the pixel value at the top left, and the second dimension is a pixel value at the top, the bottom, middle left, okay. So each dimension has a particular meaning. Okay, so collecting all these facial images in this form, and then we suddenly obtain a matrix, okay, so where rows are our dimensions or the pixel locations, and the columns are our data items. So in this case, suppose we apply some matrix factorization, and then this matrix is factorized into A and B. Okay, and then more concretely, suppose we have a 9 pixels, and then suppose we collected 100 people's image. Okay, and then typically this factorization is done in a way that it has a lower rank. Although we didn't study the rank, but we will soon study about it in maybe in 2 weeks. But anyways, suppose this guy is factorized into this form. So we have 4 columns in so this is matrix A, B, and C, and then the C is represented. So this is 9 by 4, right? And this is 4 by 100. Okay. All right, and then so what's the meaning of it? So we have 100 different facial representation in terms of their pixel values, right? 100 different vectors in 9-dimensional space. And then suppose we can factorize it into this form, which is much smaller number of column vectors, where we have only 4 columns, and then from the perspective of a column combination perspective. So by only using this common set of 4 columns, suppose 3, 1, -1, 2. Okay, so that will work as a linear combination coefficient to produce the first person's facial images, for first person's facial image as their full pixel value, and maybe -2, 3, 1, 0. And that will work as the second set of linear combination coefficient to produce the second column, right? So in this case, the challenge is, so we have 100 different columns, right? But they are actually represented as 4 different, only the different linear combinations of only 4 common columns, right? But if we can perform, if we can somehow perform or obtain this matrix factorization, okay, and then what will be the role of this columns of B? So we have 4 columns, right? So those columns should be recyclable or utilized as much as possible to represent all the different 100 people's facial images, right? So if we perform that factorization, and then we so in this case suppose we obtained maybe 30 and maybe 15 and 40 and 0 and 250 and so on, right? And then we will have a 9-dimensional vector, and then we can rearrange it into like 3 by 3 image, right? And then we can basically reconstruct or convert this vector into a matrix. And then what will be the pattern, or what will these 4 common column vectors look like in terms of their images? So these are the result from this matrix factorization. Okay, so something like this. So how can we understand this? So suppose this guy, the second one, 1, 2 position is maybe the second column that we obtained. Okay, and then so that is corresponding to this column. And then suppose the first person is putting the weight of 1, which is relatively low, and the second person is putting the higher weight on this particular column, right? So what does that mean? Probably the first person may not have much hair, right? Although that white is let's consider it as a equal of black. Black and white are reversed. Maybe I should have used the first one because that is corresponding to maybe the hair one. But anyways, the second one having high pixel values on the hair part, right? So probably the first person may have a small hairs, right? Than the second person. Okay, so that's how we decompose the given set of like 100 different images. Okay, so that way, this matrix factorization has a really interesting properties of revealing some interesting, the crucial component in our data set. Okay, and also, just to give you more interest, so this one is called the eigenphase, which was maybe proposed maybe more than 20 years ago. Okay, so this is quite old technique. But this old technique is still kind of valid and quite heavily used. And so let me just search for so yeah, I just searched for the deep learning and did an image search. Yeah, so the result evolves, but let's see. Yeah, maybe let me make it more specific. Convolutional neural net. Okay, so this is quite probably one of the widely used figure that introduces the neural net or deep learning, and then so it is still considering this facial images, and then it will do something by using this multi-layer neural net architecture, and then from here we can see that although these are not real, not looking like a real face, but they seem to be kind of some kind of a low-level patterns of of representing some edges or some blobs. Okay. And then maybe blobs may be used to represent some cheeks or maybe chins. Okay, and then this kind of edge will be used to form our edge shapes of our face. Okay, and then these are factorized form from our data. And then at higher levels in our neural net or higher layers, these patterns may become much more complicated, right? And then now, towards the later layers, it really can represent this complex shapes of a person's patterns, and these are still viewed as a matrix factorization examples performed in later layers and a little bit lower layers and much lower layers. But anyways, so this can also be viewed as kind of matrix factorization result, although they are not obtained through the explicit process of matrix factorization, but you can think of it almost they have really heavy or significant connections between them. But anyways, okay, so matrix factorization is that much important. And then in this particular chapter, we will study one basic matrix factorization called LU factorization. Okay, so the main intuition of this LU factorization is as follows. So we now consider some general rectangular matrix, and we now factorize A into the two particular matrices, L and U. Okay, and then now here, back to this case, A is equal to BC. In this case, we typically consider a particular condition or restriction imposed on both of these matrices A, B, and C. So for example, in this case, let me just make it as a kind of trivial factorization. So all x squared into x minus 3 times 1. So this can be viewed as a factorization, but this is really trivial, right? It has no, it makes no sense. Or maybe some x third order polynomial, and then some first order polynomial inverse. Okay, so that can be also another form of a factorization, right? But when performing this kind of factorization, we are kind of imposing, or we are following the restriction that each factor or each component in our product should be either first order polynomial or the second order polynomial, right? So all all the polynomials can be decomposed into first or the second order polynomials, right? So that is also another another axiom or theorem. But anyways, we are imposing such an non-trivial conditions. So in the case of matrix factorizations, we can also think of like 1, 2, 3, 4, 5, 6, and it can be just represented into this trivial form, right? We don't want that, right? And so we want to impose a particular conditions on B and C, and in particular, this LU factorization imposes the condition that so in this case, why we call it as an LU factorization is because it's represented as two matrices of an L and U, and L is an acronym for lower, and U is an acronym for upper, and lower means lower triangular matrix, and upper means upper triangular matrix. And then what is a lower and upper triangular matrix? You will see this form. So if we see this kind of pattern, so this is asterisk or star is any arbitrary value, whether it is a 0 or not. Okay, so in this case, along the diagonal, right? So diagonal has ones, and then those non-zero ones are over here. So we can think of this triangle containing non-zero part. Okay, so this triangle can be considered in the upper part. So there's a lower triangle when containing non-zero elements in the lower triangular part, and then that is called lower triangular matrix. And then if we consider only the non-zero entries on the this part, and it's called the upper triangular matrix. Okay, so that way, in the case of this LU factorization, the main requirement or condition imposed on the first matrix of an L is that this matrix is lower triangular matrix, and then this guy, although this guy is not exactly an upper triangular matrix, but it looks like our echelon form, and this is indeed our echelon form of the matrix, input matrix A. Okay, so we can view it as a kind of an upper triangular matrix because mostly the non-zero elements are in the upper triangular part. Okay, so that way we want to decompose this A into the product of the two matrices L and U, and the L is lower and the U is upper triangular matrix. Okay, and then also another condition is L is square matrix. Okay, square matrix. So suppose you are given in this example, suppose A is 4 by 5 matrix. 1, 2, 3, 4. 1, 2, 3. Okay, so you are given any rectangular matrix, and then it is decomposed into lower and upper triangular matrix. But in particular, further condition that we have is this L is square matrix. So it is 4 by 4 matrix. And what about U? To make the same size as an A, as a product, you should have the size of 4 by 5 matrix. So L has the square matrix that has the dimensions of this rows of an input matrix, and U, the size of U, is the same as the input matrix A. Okay, and yeah, one last condition is this L, as I mentioned, this upper triangular matrix, but it is saying that this L is a lower triangular matrix, but L is called a unit lower triangular matrix. What does that mean? Unit is usually meaning 1, and so this unit lower triangular matrix is, as we can see, the diagonal elements are all 1s. Okay, so when calling just a lower triangular matrix, so this can be like some non-zero elements. Okay, but the case of unit lower triangular matrix, and then all the diagonal elements are 1s. Right? Any questions about the main kind of problem setting of this lower triangular matrix? Okay, and then yeah, let me give a quick understanding of what U is. Okay, U is your echelon form of the matrix A. Okay, not the reduced echelon form, but only the echelon form. And then how can we obtain this factorization of A being equal to LU? So let me give an overview of how we obtain this LU factorization. So this is just nothing but the Gaussian elimination. So we are given A, and then we perform elementary matrix and its product. Suppose we needed 10 steps of Gaussian eliminations to obtain our echelon form matrix. That echelon form matrix is now called matrix U in the LU factorization. And now this guy, okay? We already studied that each of our elementary matrix is invariable, right? And then the product is also invariable, and then we can freely move this left part of matrix into the right part or right hand side. And then in that case, A is what? U and E inverse, E1 inverse, E2 inverse, E10 inverse. So you guys know that the inverse of this guy is like reversing the order, right? Right. So suddenly we obtained some factorization of an A as the inverse of these reversed order of these elementary matrices, and then our echelon form matrix U, right? So this will be your LU factorization. Okay. So the question is whether this guy, okay, this guy satisfies the condition of L, which is unit lower triangular matrix. At least, yeah, let's first check the size. Okay, so in the case of an A over here as 4x5 matrix, in this case, what is our, each of our elementary matrix? So elementary matrix was a square matrix, and then it is multiplied on the left, right? And so 4x4 is all the elementary matrix size, right? And then now 4x4 matrix, yeah, every elementary matrix is invariable, and so the whole product of this inverse of a 4x4 matrix will also be 4x4 matrix. So the size will not be a problem. And then now the question is, still this guy can be represented as this unit lower triangular matrix. Okay, so that is the main kind of interesting part that we will study, along with how to mechanically obtain LU factorization, right? So in this case, so it is not always true that this L is always satisfying this unit lower. This part is unit lower triangular matrix. Okay, so that condition is satisfied only when we perform our elementary matrix as row replacement. Okay, so again, in terms of different types of a row operations, we have three types: row interchanges, scaling, and row replacement, right? And then now we only allow row replacement, but not the row interchanges or row scaling. Okay, so we do not allow these two simple operations, but we only allow row replacement. Okay, and then when making that matrix into, when making the input matrix into echelon form by only using the row replacement, and then we can obtain LU factorization, which means the whole product of inverse matrix of row replacement elementary matrices. So that will satisfy the unit lower triangular matrix. Okay, so we will study more in the next class. And that's it for today. Okay, thanks. 네.
이게 이렇게 돼야지만 만족하는 건 이해되는데 그냥 이거 교재가 그냥 어려운 거라가지고 인터체인지에 대한 말만 언급돼 있어서
네네네.
근데 이게 로우 스케일링을 안 해야지만 얘가 1111을 가질 테니까.
네네네, 맞아요. 그러니까 이게 여기서 내가 한 가지 얘기를 좀 더 했어야 되는데, 그 로우 스케일링은요.
네.
로우 스케일링은 사실 어떻게 보면 우리가 엘리먼터리 매트릭스를 만들 때는 로우 스케일링은 사실 가만 생각해 보면 별로 필요가 없어요.
의미가 없는 계산이기도 하고.
그 이제 다이아고널, 그러니까 우리가 그 계산을 편리하게 하기 위해서 일단은 로우를 뭐 예를 들면 그 지우개를 우리가 1로 만들어주기 위해서 로우 스케일링을 해주고 그 다음에 지우자 뭐 이럴 수 있는데, 우리는 걔를 꼭 1로 안 만들어도 이 아래쪽을 다 지울 수가 있잖아요. 그 forward phase 혹은
그런데 이런 다이아고널 1을 만들기 위해서는 결국에는 스케일링이 없어야 되는 게 맞지 않나요?
네, 맞아요. 그러니까 이거는 우리 매트릭스 A가 아니고요. 여기 지금 에실론 폼에 있는 요 피벗은 이제 0이 아닐 수 있는 거죠.
네네.
1이 아니어도 되는 거죠. 그러니까 얘네들은 우리가 안 건드리면, 우리가 얘는 뭐에
얘네가
해당하냐면
스케일링이 돼 있으니까 여기 그 값이요.
얘는 그러니까 로우 리플레이스먼트에 해당하는, 아까 이 파트에 해당이 되는 거잖아요. 그러니까 이 파트에서는 로우 저기 스케일링이 없기 때문에 그래서 약간 다이아고널이 1로 유지가 되거든요.
그렇다면 그만큼의 스케일링 값이 대신에 여기에 녹아들어요.
네, 그렇죠. 그러니까 맞아요. A에다가 이 다이아고널 엘리먼트 혹은 우리의 피벗들을 스케일링을 안 해주겠다는 뜻이에요.
네, 맞습니다.
감사합니다.
네.
여기서 요 상황에서 요거를 개별적으로 알고 싶을 때 이거의 어그멘티드 매트릭스를 구하고 어떻게 해야 돼요?
잠깐만요. 이게 C1은 이제 컬럼이니까 C1의 인버스나 C2의 인버스는 존재하지는 않을 것 같고요.
그럼 아까 언급하셨던 게
언급한 거는 요 C가 일단은 이 관계를 만족하는 C를 찾으면 이게 곧 인버스 매트릭스이잖아요. A에. 그러면 A의 인버스 매트릭스가 곧 C인데, 근데 예를 들면 문제가 A 인버스 매트릭스의 두 번째 컬럼만 구해라 라고 하면 우리는 이 C2를 구하면 되는 거잖아요. 그럼 이 C2는 어떻게 구하느냐? 아까 얘기했던 것처럼 AC2 이거를 X로 놓고, 그 다음에 이제 B 파트를 이제 010이라는 어떤 B로 놓고 이 리니어 시스템을 풀면 되는 거라는 거죠. 그러니까 인버스 매트릭스는 원래 이렇게 100, 010
아예 그냥 놓고 그냥
이렇게
매트릭스 연산하지 말고 그냥 놓고
그렇죠. 복잡하게 풀지 말고 그냥 어쨌건 세컨 컬럼만 구해야 된다면, 인버스 매트릭스의 세컨 컬럼만 구해야 된다면 이제 010만으로 B를 놓고 풀면 된다는 거죠.
네네. 감사합니다.
질문이 방금 2.3에서 그 선형 변화는 1대1이라고 하셨는데 적어도 하나의 해를 가는 전사 변환의 경우에는 1대1이면 원래 해가 한 개이거나 해가 없다는 뜻 아닌가요?
1대1이면 해가
유일한 해가 있거나 아니면 해가 없거나가 1대1인데 전사 변환의 경우는 적어도 해가 한 개 있다는 경우잖아요.
그렇죠.
그럼 얘는 무조건
해가 하나씩만
있다는 거예요?
그러니까 원투원 and 온투가 둘 다 만족을 한다는 거죠. 그러니까 이쪽에서의 포인트는 스퀘어 매트릭스다 그러면 원투원이나 온투 중에 둘 중에 하나를 만족하면 나머지 하나도 무조건 만족이 된다 라는 뜻이 돼요.
그러면 해가 자명한 해 한 가지만
그렇죠. 해가 딱 하나만 있는 거죠.
하나만 있다는 거고.
그리고 그 해가 뭐냐? A 인버스 X라는 거죠. 그 레프레젠테이션으로 딱 하나로 이렇게 명확하게 정의가 되기 때문에 네.
2-4 챕터는 안 하는
네,
거예요?
안 해요.
이거 팩토라이제이션 할 때 여기가 왜 이렇게 스퀘어?
네.
왜 스퀘어가 돼? 이거는
아,
제가
LU 에서?
정하는 거 아니에요?
아, 네, 맞아요. 그 정하는 건데 안녕하세요. LU 팩토라이제이션에서는 우리가 그 저기 L 파트, 그러니까 왼쪽 매트릭스를 그걸 스퀘어 매트릭스로 정의하는 거예요. 그러니까 그거를 그렇게
혹시
LU
이거-
팩토라이제이션에서 프로블럼 세팅이 그런 거예요.
아 이거 이렇게 인버스로 L 만들어서 인버스면 스퀘어니까
맞아요. 네,
그렇게 생각해도 되는
네, 맞아요. 그러니까 아까 내가 예제로 들었던 뭐 4개 컬럼만 쓰자라는 그 매트릭스 팩토라이제이션은 우리가 다루는 LU랑은 맞지 않는 거고요. LU는 정의상 이제 왼쪽 매트릭스는 그 스퀘어 매트릭스가 되고 오른쪽은 오리지널 매트릭스랑 사이즈가 똑같은 거고요.
네. 감사합니다.
아이고, 안녕하세요, 교수님.
애들이 되게 열심히 하네.
네. 그봐 저기 치우겠습니다, 교수님.
아니야.